Hello, I hope everyone's having a great Narcon so far. My name is Todd Smith. I've been flying rockets for about 25 years. I believe I got born again in rocketry around the same time that Our Sky came out. I think that was around 99, somewhere in there, late 90s, early 2000s. And I found this when we got back into rockets, I didn't even know that high powered rocketry existed. And I found this awesome club in Geneseo, New York called Mars, and we started flying. My friends and I started flying with the Mars Club right around 2000, and got into high-powered rocketry. From there, I went on to join NAR and get my level one and level two cert, and I found out that I really like flying large, slow rockets. The only problem was I wasn't very successful when I first started out 20 years ago. So over the course of 20 years, I realized that there was some stuff to learn, and that's what I'm going to share with you guys today. The way that I started becoming more successful and having more successful flights was by managing the risk portion of high power rocketry. And that's what we're going to talk about today. This is going to be an introduction to managing risk in high power rocketry. So let's get started. All right. So, what is risk management? When we hear this word risk management, I think the first thing we start to think of is safety. And that's good. That's good because safety is absolutely part of risk management, but it's actually a result of risk management. Safety comes from risk that has been managed properly. So it's not necessarily safety. Believe it or not, risk management comes to us from our friends in the insurance industry. And the insurance industry describes or defines risk management as the forecasting and evaluation of financial risks, together with identification of procedures to avoid and minimize their impact. So, what does that mean? It looks like somebody's trying to save money. And they absolutely are, because insurance companies are in the business of making money. And the way that they make money is they take in more money via premiums than they spend out or expend in expenditures or payouts. Okay. So what the insurance companies like to do is they like to find ways to make sure that they have to pay out less money every single year. So they do this process called risk management, where they can figure out where they're going to spend the money and either not decide not to insure those areas or find ways that they can mitigate that risk and avoid large payouts in certain areas. In rocketry, however, what we're talking about here, risk management in rocketry is how we get from a concept to a recovered flight. How do we go from an idea of a rocket to a good liftoff and successful boost phase to a successful recovery? Well, we do that through risk management. Believe it or not, risk management is what does that for us, or at least allows us to be more successful than we normally would. The things that we're going to be talking about in today's presentation are the same things that NASA and SpaceX use on multi-million dollar rockets and multi-million dollar rocket missions to have successful missions and successful flights. So, how do we basically get to this from this without any of this or this? That's what we're going to be talking about today. And that we don't want that to happen either. We do this through risk management. Okay. So, risk management, what are we talking about when we're talking about in rocketry? Well, rocketry is inherently hazardous. Rocketry is a hazardous activity. There's really no way to get around rocketry being hazardous. Okay. So, we're taking a vehicle, we're shoving a motor in the back end of it, lighting it on fire, and controlling an explosion, which makes that vehicle now go forward at high rates of speed, reaching velocities maybe over 300 miles an hour in some cases. And then we're taking that rocket and putting it way up in the sky, sometimes 10,000 feet or more. Okay. That's hazardous. Everything in that idea is hazardous. What we cannot allow rocketry to be, though, is risky. Okay. Rocketry must not be a risky activity. And there's a big difference between being hazardous and risky. What we're trying to do is avoid this risky activity or behavior. And then we do that through risk management. And that's what we're going to be doing today. All right. So managing risk through hazard mitigation is the key to a successful high power rocket flight. If you take nothing else away from today's presentation on risk management and high powered rocketry, understand this: managing risk through hazard mitigation is the key to a successful high power rocket flight. Okay. What do I mean by that? And what are these words that I keep talking about? Well, we're going to get through most of that in this course in the next 45 minutes. So in this course, what we're going to do is we're going to identify risk through assessment, manage that risk through a couple of different things. First, flight profile planning, flight procedure development, and then redundancy concepts. We'll review all three of these things throughout today's lesson. Okay, so what are these words we're talking about? I keep talking about this hazard word, this risk word. Well, hazard, what a hazard is a thing that causes harm. Okay, it's what causes the harm to happen. And then a risk is the harm that is caused by that hazard that happens. So let's look at it like we would in a normal day life. All of us use risk management every single day in our lives. Okay. Risk management is something that we do, even if we don't understand that we're doing it, we're still doing it. We get up and we go to work in the morning. Okay. So we get up, we get out of bed, we brush our teeth, we get in the shower, we get dressed, and then we drive to work. Okay. Some activities that we do are more hazardous than others. Getting out of bed and brushing our teeth is nowhere near as hazardous as driving to work. Okay. So when we're talking about risk management in our own lives, let's check out this guy here. Climbing a ladder is a hazardous activity. Okay. So the hazard here is the fall. Because you fall off the ladder, you're going to get hurt. You're going to cause an injury. That's the risk. So the hazard is the fall. The risk is the injury. But we can prevent most of these things. Okay. We can prevent the fall and not have the injury, which is the risk, if we do a couple of things to prevent that from happening. And that's risk management. Okay. So, risk management here, when we're talking about our ladder climbing, is first off, let's start at the bottom of the ladder by making sure the ladder can't kick out. If the ladder kicks out, then I'm going to fall. If I fall, I'm going to get hurt. But if I stop that ladder from kicking out, I'm not going to fall and I'm not going to get hurt. The next thing I can do is make sure that these locks or dogs are locked on the rung and in place properly so that ladder can't slide back down towards the ground, causing me to fall and then get hurt. So I can stop that from happening. And then the third thing I could do here is not carry a tool while I'm climbing the ladder. That way I can keep 3 points of contact no matter what rung I'm on. I always have 3 points of contact because I don't have to take one hand off to carry a tool. That's risk management in real life. We can apply these same concepts to everything we do in life, including rocketry. So, what's risk assessment look like in rocketry? Okay, assessing risk identifies what can go wrong during a flight and how likely it is for that what to occur. How likely is it that this thing could go wrong? There are a lot of things that can go wrong in a flight. Okay, we're going to break some of those down today. How likely is it, though, that one of those things is going to happen? Because some things happen a lot more often than others. I'll give you an example of that. Ignition failures happen a lot more often than motor cados. Okay. All right. So risk assessment basically determines hazard potential because how likely it is to happen, how likely that bad thing is to happen is what we call hazard potential. Now, that hazard is something that can go wrong. And as we said, a lot of things can go wrong. So what we need to do is perform this risk assessment to identify those hazards or those things that can go wrong. Okay. And then finally, what we do after we've identified those things is we do an evaluation of their potential impact on the flight itself. So, to identify those hazards and evaluate risk, we got to understand a couple of concepts. We got to break the actual flight down or rocketry down into a couple of different ideas. The first being flight profile. Okay. So, every rocket flight has a profile. Hopefully, the profile that your rocket takes after you light the igniter or the motor ignites is the profile that you planned on it going up. And hopefully that starts out with one, the motor is ignited using an electronic source. Two, the motor comes up to pressure and we have liftoff where the rocket comes off of the rod and the rocket at that point is accelerated fast enough that lift is being generated through aerodynamic force on the fins and the rocket goes into a stable trajectory. It goes after the motor burns out, goes into its coast phase, continues upward in a normal trajectory until gravity and air pressure slow the vehicle down at the top of its arc. We call that apogee, and the vehicle then transitions into its recovery phase. A recovery device is then deployed. The vehicle falls stably under that deployed chute or other recovery device until it softly touches back down on the ground. That is a nominal flight profile. Okay. So we're going to be talking about flight profile planning and identifying things that could go wrong in our flight profile. The next thing is flight dynamics, okay? What forces create a rocket flight? What makes the rocket go forward? What makes the rocket have stability when it's going through the air? What forces are against that rocket? And what forces change as that rocket changes in velocity or changes in uh, 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 direction of attack? Okay. And the next thing is vehicle dynamics. What are the parts of the vehicle? Every part of a vehicle can fail. So we need to be able to identify those areas that have potential or higher potential for failure. So our vehicle dynamics are just as simply as understanding the body tube or the airframe, our fins, our motor mount. We could have failures in any one of these points. Our shock cord could break, causing a separation where the rocket body comes down on its own and then the nose cone drifts off to the rocket gods. Okay, so we need to understand every component of the vehicle, and when we're doing these risk assessments, we need to identify things that could potentially go wrong along with each one of these parts. All right, so as flight complexity increases, guess what else increases? Flight risk increases. But it doesn't just increase one for one. So, in other words, if I double my complexity of my flight, I don't just double risk, I quadruple my risk. All right, that's an important concept to understand. So, now if we go back to the same flight profile that we had talked about earlier, now we're going to look at a different flight profile, a two-stage flight. So, what I've done now is I've increased the complexity of my flight profile. And in this case, I've got a three-stage rocket. First stage has to ignite, come up to pressure, move the rocket. The second stage has to ignite after the first stage burns out, come up to pressure, continue to move the rocket. The third stage needs to ignite. So now I don't just have one ignition and one boost phase, I have three of those. But I haven't just tripled my risk by increasing that flight profile, okay? I have exponentially increased the risk because each one of those problems could pop up at any given time. And the more times I'm trying to do something that could cause a problem, the more potential for a problem I have, okay? Flight dynamics will also, risk will also increase exponentially as our flight dynamics change. If I'm having a nominal flight, a subsonic flight, that's going maybe to an altitude of 4,000 feet, I'm going to have way less risk than if I'm doing a supersonic flight that's projected to go 12,000 feet. Okay. This is for a bunch of different reasons. Okay. Because more things can go wrong with not only my flight profile in this case, but more things can go wrong with the dynamics of my flight as well. Okay. If my angle of attack changes for some unknown reason, maybe a broken or a chipped nozzle, or something goes wrong in the aft end of my vehicle, and that angle of attack changes by a couple of degrees, and the rocket is traveling subsonically at, let's say, 250 feet per second, I'm not going to have the same impact that I'm going to have when I'm moving supersonically and I have that small change in angle of attack. One, the rocket might go off course. The second one, I'm probably going to see a shredding event in my vehicle. So now that flight risk increases as the flight dynamics increase or get more complicated. The same thing happens with vehicle mechanics. So my vehicle before, my Estes Alpha that we had showed when we were talking about the parts of a rocket, now I have double the amount of parts in my rocket because I have a two-stage rocket now. So now I don't just have one motor mount, I have two. I don't have one fin can, I have two. I have multiplied the number of components that can go wrong or fail during my flight. So flight risk increases exponentially every time we increase the complexity of our flight or our vehicle. Okay, so we can see that in this chart pretty well. If we look at this dark blue line here down at the bottom of our graph, that's complexity. And you'll notice that that dark blue line at the bottom of the graph doesn't move very much off of zero. In fact, it comes up very subtly all the way across the left-hand side of our graph here. But look at what risk does. Risk takes off immediately, okay? And starts charging away from that complexity line to the point where it takes a huge arc and looks like it's surging almost vertically off of that complexity line. That shows us how the exponential portion of that risk increase happens as complexity increases. All right, so this final step in our risk assessment is the risk evaluation. So, how do we evaluate this risk? How do we give a value to it? Okay, if I don't have something tangible that I can actually touch and feel, it's probably not going to be real. So, I can't just say, well, that's a high risk or that's a low risk operation, because the other thing that happens there is we start talking about things subjectively instead of objectively. People have opinions. Okay, some people think that you can't air start motors. Some people think that the only way to do a staging event is through air start, so on and so forth. Okay. People have different opinions on how to do different things. So if I was to make this risk assessment just subjective, we really wouldn't get anywhere by doing it. What I need an objective, absolutely objective risk assessment that can give me a value, a tangible value that I can look and see things. All right. So what we want to do is we want to find out what could happen, how bad would it be if it did happen, and how often is this thing that we're talking about, this hazard, expected to take place or happen. And what we need to do again is go back through and figure out this risk assessment and bring a value for the potential for something bad to happen for every one of those three parts we talked about before. We want to understand it for our flight profile, our flight dynamics, and our vehicle mechanics. So, what could happen? That's going to identify our hazards. We go through all of the vehicle parts, uh, all of our flight profile ideas, and then all of the possible flight dynamics that the vehicle could be in when it's in that flight profile, and identify things that can go wrong. Okay, and we'll get to that here in a couple of minutes when we actually look at a rocket. And we'll just start talking about and identifying some things that can go wrong. But what could happen is an identified hazard. That's what we're doing when we're doing this risk assessment. We're looking for each one of those things that could go wrong. How bad it could be, that's going to identify our severity, okay, or our impact of the event. Some things are going to be way worse than others. Uh, some hazards have a larger impact than others. How bad it could be is measured in that severity. If I had a rocket that failed to put its chute out, okay, and it lawn darted back into the field, that's a bad situation. It's a very dangerous situation. That's bad. But it could be way worse had it gone over the flight line and back into the crowd. So those are different levels of severity. And then how often it's going to happen is something that we call frequency, or the likelihood that that event is going to happen. So we take all of these separate things and plug them into a chart or a matrix that would look something like this. And then that way we can get a value out of that exact operation. So let's talk about a couple of different things that could happen on the rocket field. There's some things that we have seen before, or some things that have pretty good potential of happening, and we'll give a value to those things. We'll find out what that actual risk is. So something that happens all the time, or likelihood, would be measured over here on the left hand side of our matrix here. Okay, so, and if it happened all the time, we would call that probable. If it happened once in a while, we would call that occasional. And if it didn't happen very often, or probably not much at all, or maybe won't ever happen, we call it improbable. At the top part of our matrix here, we have our severity, or how bad the impact is going to be, starting out all the way over here on the right with marginal, uh, something that's not too bad, moderate, a little bit worse than not too bad, but it's not really good either, and then critical. Okay, uh, so we'll measure our severity in those three markers. So let's choose an event now. So my event for this will be, let's choose an ignition failure. Okay, so that's something that we see happen on the field all the time. We see igniters that fail for one reason or another. There's usually a really good reason why it did fail, and almost in the modern day event, after especially after Estes has fixed their most recent igniter, we'd almost never see that it's a manufacturing failure, or those are almost the least amount of failures. So we can, that's something we can fix. We'll talk about that when we talk about fixing or managing risk in the second half of this program. But ignition failure is something that happens quite often, so it's probable that it's going to happen. But what is the severity of that? What is the actual severity of that ignition failure? So if the igniter never lights or never lights the motor, really, it's marginal. There's almost no impact. But you'll notice that it still has medium risk. It has medium risk because it happens all the time. And the reason why in our chart it ends up being a medium risk is because every once in a while, that igniter not just does it fail, but it fails to ignite the motor properly. If the motor doesn't build up pressure inside of the chamber and the motor begins to chuff on the launch pad. Even though the motor is chuffing, not producing thrust, the rocket hasn't lifted off yet. We have started that delay grain, and that delay grain starts burning upon the chuff of the motor. Eventually, the motor comes up to pressure, builds enough thrust where the rocket takes off into the air. And what happens immediately after it leaves the rod? At its maximum speed, it puts out the shooter, that puts out the chute. Okay. All right. So that is a situation where maybe something could happen to the vehicle, and it does maybe a damage zipper to the vehicle. Okay. But in most cases, 9 times out of 10, the igniter not lighting means that nothing is going to happen. Now, let's look at something that happens occasionally. So occasionally, a motor would explode. All right. So we have a CATO event in our right at ignition. Okay. How often does that happen? I've seen you guys comments here on the yeah, unless you're wanting to ignite a cluster motor, absolutely, yeah, all of those things, right? Yeah, so that's why when we talk about it being marginal, right? Even though it's marginal there, it's still a medium risk because bad things can still happen with an igniter not working properly. A bunch of bad things, and that's why you don't see it being low risk because something could happen. And again, it's medium risk because it happens all the time. Let's jump right down to our motor CATO. So it happens occasionally. What is the what's the worst that could happen? So the worst that could happen, hopefully, if everybody's in their proper locations and they are behind the flight line, and we have our proper distances from the actual rocket itself, nobody should be getting hurt. Right? Could happen though. Could absolutely happen. But probably it's going to be marginal to moderate. Okay, because at worst, it's probably going to destroy the vehicle. Now, if I'm talking about the vehicle itself, the vehicle is going to be lost, and I have all my time and effort into that vehicle, not and a lot of money into that vehicle, probably more than likely. Then that's going to be a critical failure. So I'm going to be somewhere in this medium with my severity of that. Okay, now let's talk about we're doing a dual deploy flight, and I'm using electronics for my dual deploy operation. And so, in other words, everything's going to be black powder fired using electronics instead of chute release. How often do we see a failure in one of those operations? Well, if we had to look at data for dual deployment flights, I would say that it is quite probable that there will be an issue with one of our events, either the main or the drogue event itself. Okay, so it's probable. What's the worst thing that could happen here? Well, the rocket comes down and comes in ballistic and impacts a car, maybe breaks a window, or even worse, injures somebody. So we could be moderate. So when we're flying dual deploy, high powered rockets, notice we're in the high risk area here. Okay, but that's how we figure out whether or not or we give a value to something because we're not worried about being subjective here. We're being objective. And these severity charts or risk assessment matrices, I should say, they can be broken out into a lot more than just 9 boxes. We can break these things out into many more areas where we can get medium to moderate, high to low, so on and so forth, all the way through. All right, so let's do an actual risk assessment here on a high power rocket. So we got our high powered rocket here. We're going to figure out what our flight risk is going to be for this vehicle itself. We're going to figure out is it going to be low, moderate, high, so on and so forth. All right, so again, we got to do that once again for the flight profile, for the flight dynamics, and the vehicle mechanics. So this is again a high power subsonic flight with dual deployment. Okay, let's take a look at our chart and go through this real quick. All right, so flight profile. What do you think on flight profile? Do you guys think that a high powered subsonic flight with dual deployment? Um, do you think this flight profile that something goes wrong with these type flight profiles all the time, occasionally, or sometimes? Well, in our flight profile, we said that we are going to have uh, dual deployment. So we noticed that dual deployment, sometime between occasional and probable, we're going to have an event happen. Okay. What is going to be the impact of that event? Well, hopefully it's just marginal. And we put the drogue out and fail to get the main to come out. And then the rocket slams the ground at a hard impact. So that more than likely is going to be at least a moderate risk. So I have a moderate risk flight profile here. How about flight dynamics? Well, the vehicle is going to be subsonic. It's not going to be going supersonic. I'm expecting very nominal impact on the vehicle during flight. So I'm probably going to say something bad happened because of my flight dynamics is pretty improbable here. As long as I'm flying within the windows that I know that the vehicle can fly in, which is something we're going to be talking about in risk management. Um, but occasional something might happen, like it maybe a gust of wind comes up that I didn't know about it. But at most, what's going to happen? Maybe put the rocket off course. So I'm probably going to be over here in this low area again. Now, vehicle mechanics. So I have a bunch of systems on board this vehicle. I have my avionics bay that sits right here. I have dual altimeters in here, and I have a total of 4 black powder charges. And that's 4 sets of wiring that are in there, 2 batteries that are in there. Okay. I'm trying to make sure that nothing bad is going to happen. But I've increased my complexity on this flight because no longer am I just flying a rocket with a simple motor ejection charge. I'm flying a rocket now that's worried about 2 computers to make something happen. So this now could be really bad because it's probable that something could happen. All right, we just identified that. And if nothing happened here and I had a total failure in my system, I could at least have a modest critical impact if this vehicle comes in ballistic again. So all right, so my vehicle mechanics here, they're going to get the absolute high risk operation. Okay, so what does all this mean now? I've identified that my flight profile is a moderate risk, my flight dynamics are low risk, and my vehicle mechanics are high risk. What does that mean? All right. Well, it's going to mean that we need to definitely address vehicle mechanics when we get to the risk management portion. And that's what we're going to go into next. All right, so managing risk. How do we manage this risk that we've identified? Okay, well, we've got to develop some method to manage that risk and mitigate it. We can't eliminate all risk. It's almost impossible to eliminate all risk. Some risks can be eliminated, but those that can't still have to be managed. And we do that through some form of mitigation. Okay, so when we're talking about flight profile, we can plan our flight profile. And we do that by planning by each different phase. Okay. So we got our ignition phase, we've got our boost phase, we've got our coasting phase. Then we transition to apogee when it's getting ready for recovery. We get that initial recovery device out. Our primary device slows the vehicle down for a nice soft landing. And then we finally get our hands on the rocket and bring it back to our tent. How do we plan to manage each one of these things? And there's a lot of different things that we can do for each one. I'm just going to show you what a typical flight profile planning looks like for that flight that we just talked about. Okay. So the flight profile planning, it's going to reduce the risk of each one of these phases by selecting methods that have the highest potential for positive outcome. That's what we're trying to do here. We're trying to create the highest potential we can for a positive outcome. When it comes to ignition, we want an initiator capable of instantaneous ignition. Okay. Motor chuff is an enemy. We just described that, what that looks like. Okay. It can destroy my vehicle. It can cause the vehicle to burn on the launch pad. All right. There's a bunch of different reasons for that. One of the most common being is that the most common motors we use in high power rocketry today are CTI and Aerotech. Okay. CTI motors come with a black propellant slug that's in the top of the motor, the forward part of the motor, and that helps with ignition. You can use an E-match. The E-match ignites the black powder slug, which ignites the propellant, brings the propellant up to temperature and pressure inside of that chamber. If we try to use an E-match in an Aerotech motor, it simply won't work because Aerotech motors lack that black powder pellet to help with the ignition phase. So the E-match would burn and maybe light a little portion of a grain, but never light the grain enough to build up pressure and create a flight. So we want to make sure that we're using the correct initiator with the correct motor. How do we do that? The only way to do that is to have a written procedure with a checklist that says, I'm using an Aerotech motor. I've got to make sure I have my Aerotech igniter. I have seen this happen on the field time and time again. In fact, just last year, we had a gentleman who was trying to get a rocket off multiple times, and the igniter was firing. We checked the electronics. We checked everything. We checked the firing system. We checked everything. And he finally came back to my tent with the last igniter that he had, and he says, yeah, it burned. I don't know what's happening. So, and at that point, I realized, because I had paid attention this time to the call out, well, here we go again. And he was trying to light an Aerotech motor with a E-match. It just simply wasn't going to work. Okay, so now to the boost phase. How do we create a good boost phase, right? How do we make sure that the rocket's going to go the way it's supposed to? Well, we want to make sure that we have a thrust ratio of at least 3-to-1, but closer to 5-to-1 is the preferred. But what makes that thrust ratio absolute is we need enough thrust to get the vehicle going fast enough that the fins can create lift to make them aerodynamically stable as the vehicle comes off of the launch rod. How do we figure this out? How do we figure out if we're going to have enough? Well, back when I started this thing back during the October Sky days, we did this all either with by hand with actual calculations. We even would do the old Barrowman equation ourselves on paper, or we had a DOS form of Microsoft software that we could punch a couple of numbers in and hopefully give us an idea of where it is. Today, it's as easy as going onto an app. We can find apps on our phones. We have RockSim. If you don't want to pay for RockSim, we have OpenRocket. There's ways that we can simulate these vehicles before we put them out on the pad to make sure that everything is going to be in good shape there. Okay, vehicle stability. How do we make sure that it continues on that trajectory? Well, again, that's planning and going through our simulations. A lot of things can change. One thing we know is going to change is that the motor's going to burn out, and as that motor burns out, the weight's going to change in the back end of that rocket. Another thing we can have happen is something called payload shift. So payload could shift down the rocket, or excuse me, the parachute moves down inside the rocket, maybe just 1 or 2 inches, but it's enough to change that center of gravity, and then the center of gravity gets closer to that center of pressure, and we become a neutralized stability rocket, and then we're not going to have that great flight. That picture that we showed earlier where the rocket went straight and then all of a sudden went all over the place, yeah, that's because center of gravity changed mid-flight. Something went wrong there. Okay, we can plan for that if we have a rocket that's hopefully more than 2 caliber stable. But if I start worrying about getting down into that caliber range where I'm 1, maybe even 0.9 caliber stability, then I got to start worrying about winds and what the maximum wind is I can fly in. Timing of apogee event is another thing, right? So we can use our software to give us that good timing of apogee. We want the event to happen as close to zero velocity as possible. We don't want it too early, and we don't want it too late. That's just going to cause vehicle damage our recovery device, and now we're in more trouble as we head down into that initial recovery phase. Okay, so initial recovery, that first event that is going to prepare the vehicle for descent, where we're breaking the stability of the vehicle, breaking it into 2 or more parts, so the vehicle is no longer stable and can no longer fall back down in a stable trajectory. How do we do that? Well, we do that through redundancy, which we'll talk about redundancy here in a second. Primary recovery. So we want to get a shootout that's going to slow this vehicle down to 15 miles an hour, 20 feet per second, whatever your target is, but we want it to be hitting the ground at a speed that's not going to cause damage to the vehicle. And then our final recovery there is the ability to locate the vehicle after the vehicle touches down. Okay, this is so critical, especially if you're flying on a field that has high vegetation growth, or maybe there's crop planting such as beans or corn. I've seen Large rockets, 12-inch diameter rockets, 15 feet tall, disappear into beans, even with a large parachute. I've seen cornfields eat parachutes as large as 20 feet in diameter. Okay. So we need to have some radio tracking device or some GPS device that's built into the vehicle for even after it touches down. All right. So procedure development. That's our next step. Procedures, 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 procedures. NASA, SpaceX, they would never think about lighting a motor without a procedure. Okay. And we need those procedures for pre flight simulation, pre flight inspection, motor preparation, recovery preparation, flight minimums, which is that wind or environmental impact, and then pad preparation. And then a final go or no go, critical to what we do with rockets. Okay. These procedures provide the only link between intention, all right, and action that are capable of bypassing emotion. I can't state that enough, okay? Go fever is a real thing. You worked for months on this rocket, you built it all winter. We finally got to the spring launch, the first spring launch, and you get the rocket up on the pad. Several things have gone wrong already. You couldn't get maybe the nozzle to screw on properly. You got through that. You couldn't get the shear pins to lock up properly. You got through that. You got through all these problems, and you get to the pad, and one more problem pops up, and you can't get the pad angle that you wanted for that day. Say no, stop, don't go. But the only way that you won't go is if you have a procedure that says yes, you can go, or no, you can't go. So pre-flight simulations, they define our flight parameters for us. We're going to find out in those simulations what winds my vehicle can take, how stable is it close to neutral stability, or is the vehicle overstable? Winds are going to affect, weather is going to affect both of those. Or is my rocket going to go 10,000 feet? Okay, we want to know all of those things. What is the waiver? All right, is my waiver at 10,000 feet and the rocket sim to go 10,000 feet? That's a no-go. We need to change something differently there. Pre-flight inspections, that's a mechanical problem finding exercise where we try to find hazards or things that can go wrong with the vehicle before we launch the vehicle. This is where we're looking for those loose launch lugs or a broken fin or something that's wrong with the motor retention system. Motor preparation. All right. So you want to create a consistency in a controlled environment. What I do with all of my motors is I build them all in my rocket shop before I go to the field. I never assemble a motor on the field. I do that for a couple of different reasons. I have procedures for every single motor that I fly. That procedure is built off of the manufacturer's instructions, okay? But it's a step-by-step procedure with check boxes that I have made for my own uh, self to build the rocket off of my own check procedure in my environment. And this way, I don't have people talking to me. I don't have something crazy going off on the pads that I want to watch. Nothing distracts my attention from putting that motor together the way the manufacturer asked me to do so. Recovery preparation, done the same thing. I do all of these things in my shop. This way, I ensure that no step is missed or overlooked. And in our procedures that we have written for recovery, we actually include a step called picture taking, where we actually take pictures of the D-links, the D-rings, when we connect them to the bulkheads and when we connect them to the parachute, so on and so forth, so that when the rocket's on the pad, we can go through one final check and say, oh yeah, that's connected, that's connected, that's connected. I've seen some of the best flyers in this country take large rockets and drop them simply because they forgot to close a D-ring on a parachute. Flight minimums. So this is where we match up the environment with what our simulation said we could do. Simulation said that this rocket can fly in 12-mile-an-hour winds. It's 15-mile-an-hour winds. It's a no-go. Pad preparation. I take a checklist to the pad with me to make sure that I'm combating that flight fever. I don't want that go fever to happen. So I have to be on the pad checking my little boxes saying, yep, this rocket can fly. This one, this rocket's expected to go to 8,000 feet, and I have a 7,500 foot cloud deck right now. The ceiling's at 7,500 feet. First off, it's illegal to fly into a cloud. Second off, I don't want to take the chance of ever putting it up there, even if it wasn't illegal. And that's when I get into my final go, no go. It's a final set of checks that when I am standing on the line and they say, Todd Smith, are you ready to go? I can either say yes or no. Okay. Don't ever be afraid to say no. I've heard horror stories. Just this week, I had somebody tell me a story about how they lost a rocket in a certain location and they had a tracker in it, but the tracker battery died as it was sitting on the pad. I had another situation last year where we were talking about a motor that we knew had one of those pellets in it that was a little bit too large for what the motor could handle at the onset, and it was blowing a lot of nozzles out. We talked about it, and just before the rocket took off, they didn't do anything about it. The motor blew up, and he came back to me later and says, "Man, I wish I pulled it off the pad." Don't let that fever, that go fever, take you off of what you normally would do, making a normal, rational decision. Okay, that's your final flight. No go, go chase. All right, so now redundancy concepts. All right, this redundancy concept is an engineering concept that provides additional equipment not necessary to the absolute function, but allows for recovery of the fundamental functions should we have a failure there. So basically what we do is we want to back up every critical vehicle function. All right. These functions are critical to the vehicle survivability, basically. All right. So it says here propulsion is not a function critical to vehicle survivability. I almost took this out, but I thought it was a good point to have this little quick conversation. It's not, because if it doesn't light and it doesn't work, then the vehicle's not going anywhere. However, what if you're trying to light a multi-stage vehicle? Or what if you're trying to light a vehicle in a cluster form? It absolutely is, but we don't have a way to back up propulsion. We don't put extra motors on our rocket in case the rocket motor doesn't light, and that's more or less what I was talking about. We want to back up the critical recovery function so that the vehicle can survive coming back down. Okay, so these components are critical. Components critical to the recovery should be duplicated. How do we duplicate that? Well, we back up motor ejection with electronic ejection, or vice versa. You only have one altimeter in your vehicle, back it up with the motor ejection. So many times I've heard guys say, "Yeah, well, I'm flying electronics, I don't have my motor ejection in." No, use it to back it up. And even if you have two electronic devices, back it up with a third device, the motor ejection. Don't even set the delay. Let the motor come out. If that's the last thing to ever happen, at least I actually saved a rocket like that 2 summers ago. Electronic ejection is backed up by a second electronic device. And then accelerometer electronics are backed up by baro. That's just a way that you could do it. I'm not saying you have to do it. I don't ever use accelerometer electronics backed up by baro. I use 2 RRC3s every time I fly. So I just use 2 baros. But that's basically how you back things up. All right. Now, lastly, what we're going to talk about is ground testing. And any mechanical operation that is planned during the flight must be tested on the ground prior to the flight. Okay. That's apogee events, air start ignition, booster set, main recovery events, booster recovery, any event that you expect to happen in flight, you want a ground test. All right. And the conditions of that ground test must match the planned operation. I can't state that enough. If you're going to have a chute in your vehicle, then you want the same chute that you're going to have during the flight in it when you're ground testing. And that includes the protector, the harness, the same shear pins, the same everything. And lastly, record what that setup was and record what the results were. All right, so here's a quick example of me ground testing.
All right, test the drogue deployment, Frenzy XL, 3 grams. Going in 3, 2, 1.
All right, now I had previously tested 2 grams, and 2 grams didn't go very well. So I put 3 grams in here. But you can hear me in the video stating how many shear pins in here. I don't think I had shear pins. And how many actual grams of propellant I'm using.
All right, it's going to be the test of the main.
Now this is testing the main.
3, 2, 1.
And in there I said exactly how many grams of black powder I had, and I had the same a number of shear pins. And you can see this is how my rocket was packed the day that I flew it, and I had a successful flight with this rocket because I set this up the same way on ground testing day that I did on the flight day. Now, I hope everyone got something out of that presentation. It was very much an introduction to the concept of risk management. This could be an 8-hour course if we got into the ins and outs of it. So this literally was a 45-minute introduction into it. If anyone would like more information on this, or you would like to see more PowerPoints, more videos on this topic, contact me here, Todd Smith, trs027@gmail.com. Put in the in the top Narcon, and then I'll know that I need to contact you or open that up. Okay. So 5 seconds left. I hope everyone had a good presentation. I hope you're having a good Narcon. We made it. All right. I'm just going to read real quick for any questions. Yeah. Yeah, igniter and ignition failures. Yeah, exactly. Yeah, you guys had a bunch of good questions here, or good comments, I should say. I don't see any questions. Has its day. Yeah, I like that. Every rocket has its day. It need not be today. Yep, I like that. I really like that, Mark Wise. That's a wise statement. All right. Any other questions? Throw them in the comments now. We're in your session here. Beautiful. All right. Thanks, Bob. Questions, Q&A. All right. Thanks, Frank. I appreciate that. In general, multiple recovery systems are mitigation. Yes, they are. Yep. Yep. Multiple electronics increase it. Yep. Absolutely, Steve. Yep. Oh, great question here, Vince. How do you assess the need for redundancy against complexity? It adds. Yeah, it does, right? Isn't it that's a conundrum of risk management? So, in adding a second altimeter, I'm adding second wiring, I'm adding a bunch of other stuff. What I have done, in if you guys reach out to me, I'll show you like the second half of this presentation, so to speak. I can show you two av bays right next to each other. One has like there's 16 points where it could possibly fail. And then what we did was we took that 16 points where it could possibly fail and got it down to like 4. So even though it was more complex, once we started looking at points, and you know how that works is simply by every time there's a wire connection, place it could fail. All right. So don't have any wire connections. Have the wire come directly out of your altimeter right to the charge. And we can show you how to do that in the next class. We just kind of ran out of time here. And then there's a lot of RSOs going on. The RSO wants to change your rocket, do something their way that makes it less safe. How do we stop this? That's a great question, Bob. I don't know how we stop that. I just don't know how. I've run into that several times. When it's the RSO, that's the big problem. Luckily, most of the times I've run into a situation like that, it's been the LSO that wants to change something, and I grab the RSO, explain to the RSO what's going on, and they usually side with safety. But okay, did I touch on the stability of squatty rockets, base drag? I did not. I just talked about these things in general. Okay, but now what I would do for the squatty rocket, right? That's going to throw up some hazards. That's going to throw up some what we call red flags. It's going to increase our risk. So we have to find things to manage that. The only way to manage that, if we're going to fly those squatty rockets, is by flying inside of those flight parameters that I talked about. So those flight windows, and that's what our big brothers do with their NASA and SpaceX rockets. They fly in windows, right? So we need to fly in windows as well. If you've got a short squatty rocket that likes to wiggle its way up, we can't have anything that's going to impede on that like wind. So we got to stay right inside of those windows. All right. Any more questions? This is my first time doing this, so I don't really know how this goes. I mean, I've gone to this NARCon before, so I have been in the presentations, but I've never done a presentation. This was a lot of fun, though. Okay, I don't see any more questions coming in. So I will let everyone get off to their next speaker and next breakout session. And again, please contact me right there, TRS027. That's my personal email address. So contact me if you'd like to hear more about this. I want to thank everybody for joining us today, and I want to thank NAR for hosting this, and Todd and Ed LaCroix. You guys do a great job with this, and I just really appreciate the opportunity. Thank you. You guys all have a great day.